Okay, now let's turn to a way to visualize electric potentials and to relate the electric fields and the electric potentials. So maybe some people recognize this picture. This is a picture of Mount Fuji. Um, and something you might notice about Mount Fuji is that it's actually pretty steep. What next? So those of you who really enjoyed studying geography maybe came across contour maps. People who like to bike or exercise outside maybe also find contour maps useful. So what a contour map is, when a geographer draws a line that's at constant height, probably relative to sea level. So everywhere on this line, you're 2,000 meters above sea level. So you can draw it in a 3D picture or you can do a 2D picture. And then the next line is 2250, 2500, 2700. You might notice that those are all evenly spaced in distance. And then if you look at these contour lines, in some places the red lines are really close together, and in some places they're pretty far apart. So the change in distance between these two lines is the same as the change in elevation between these two lines is the same as the change in elevation between these two lines. So you get the same change in elevation, but these two are really close together and these two are really far apart. That means this is not very steep and this is really steep. So if you were walking or biking, this would feel more difficult because you change elevation so quickly. So we're going to use this idea of a contour map and apply it to electric field and electric potential. Okay, so that's the concept we're going to use. So let's start by doing a firm definition. We've mentioned this a couple of times already, but now let's get a proper definition in. Let's get a definition of equipotential lines. Equipotential lines are lines along which the electric potential is constant. Okay? So everywhere along a given line called an equipotential line, the potential will not change at all. Equipotential lines are always evenly spaced in potential. So maybe they're 10 volts apart or 100 or 10,000, but they're always evenly spaced. Let's apply this thought to a capacitor, and let's see if we can draw the equipotential lines for a capacitor. Something we're going to remember about a capacitor is that the electric field between the plates of a capacitor is constant. Okay, so that's something we know. So how are we going to draw our equipotential lines? Well, let's figure out our potential at some distances relative to our negative plate. So we take our coordinate system so that coordinate S is equal to 0 at the negative plate. And it increases as we go towards the positive plate. From negative to positive is our S distance. Let's calculate the electric potential for some values of S. We'll use the equation V equals E times S. E is the magnitude of the electric field, and S is our distance from the negative plate. And let's say in our example, we know that we have an electric field equal to 100,000 newtons per coulomb. So if we are a distance of 0 from our plate, then V equals E times 0 equals 0 volts. So anytime we are 0 meters from our plate, we get a potential of 0. So here is 0 meters, here's 0 meters, here's 0. Notice it doesn't matter where we are vertically, it's the horizontal distance that matters. So wherever we are on this line that matches S equals 0, that's where the potential is 0 volts. This is an equipotential line. Everywhere along this line the potential is constant and equal to 0 volts. Okay, let's do our next one. What if S is 0.25 millimeters? Then our potential at this line will be 100,000 newtons per coulomb times 0.25 millimeters to get 25 volts. So anytime we are 1/4 of a millimeter away, so anywhere along this line, the potential is 25 volts. This is another equipotential line. For my next distance, 0.5 millimeters, the potential will be 100,000 times 0.5 times 10 to the minus 3 to put it in meters to get 50 volts. Our capacitor spacing is 1 millimeter, 0.5 millimeters then would be right in the middle of the capacitor, and we're 50 volts. At 0.75 millimeters, the potential will be 75 volts. And at 1 millimeter, right at the positive plate, the potential will be 100 volts. So these are the equipotential lines. So these dashed lines we drew in purple, the lines that show constant potential, are the equipotential lines between the plates of a capacitor. So just some things to point out here. Let's see. We might see that our equipotential lines are all vertical. Our electric field lines are all horizontal. So our equipotential lines, EPL for shorthand, they're always perpendicular to electric field lines. That was something we showed with the math, and now we see it here in the picture. We know our electric field points from high potential to low potential. Okay, and that's certainly true. Goes from 100 volts towards 0 volts. E points towards low V. We always space our equipotential lines evenly in potential. I know we wrote it above, but let's write it down again. That one's pretty important. And just as an extra note, often when we do problems where we think about equipotential lines, we're also going to apply the analysis. So we'll say we also use that our electric potential energy is Q times V, our work done is minus delta U, and we often apply conservation of energy as well. Okay, so these will just be an extra note to help us with our problem solving strategies. Okay, so this is for between the plates of a capacitor. We often have point charges, so let's look at the equipotential line representation around a point charge. So what if we wish to think about electric potential around a 10 nanocoulomb charge? Let's put in brackets that we're talking about a point charge. And we'd like to visualize this. There are a couple of ways to do this. One acceptable way certainly is we could do a graph of V versus R. So if we put potential on the vertical axis, we put distance from a center on the horizontal, distance from the point charge on the horizontal, we know that V is KQ over R. The graph would look something like this. So this is certainly a valid way to visualize our electric potential, is just to straight up draw a graph. But we can also draw the equipotential lines. That can be really useful. We can do the same thing as we did with our capacitor. We'll just do a little switcheroo here. With our capacitor, we gave ourselves a list of distances and we found potential. This time we'll give ourselves a list of potentials and we'll find the distance, so we'll know where to draw the lines. Okay, so we can certainly do this. So what we'd like to do is calculate the distance from the charge for which the potential is constant. And we'll start with a value of 2500 volts. So we know that V is K times Q over R. We'd like to find the distance for which we know the potential. So R is K times Q divided by V. If V is 2500 volts, then R is K, 8.99 times 10 to the 9, times Q, 10 nanocoulombs, so 10 to the minus 9 coulombs, divided by V. We said we were going to start with V equals 2500 volts. And we would see that any time we are a distance of 3.6 times 10 to the minus 2 meters, the potential will be 2500 volts. What's the shape of this? Well, anytime we have a constant R in 2 dimensions, that's a circle, we want to think about 3 dimensions, so it would be a sphere. So our equipotential for V equals 2500 volts is a sphere with radius R equals 36 millimeters. Okay, we can draw that. So let's draw our first one. So our R value in millimeters is 36. So anytime we are 36 millimeters away from our sphere, so here's our charge Q. Just make sure that's nice and visible. So anytime we're 36 millimeters away, in 2D we'll draw a circle. If we could draw 3D, we draw a sphere. We're at 2500 volts. Okay, what if we were 5000 volts? We'll do the same sort of analysis and find that 18 millimeters away, the potential is 5000 volts. What about 7500? Remember, they have to be evenly spaced in potential. That happens at a distance of 12 millimeters. 10,000 volts, that happens at a distance of 9 millimeters. Okay, I'm not sure I can write small enough to get in there. I'll do my 10,000 with an arrow. And then 12,500, that happens at a distance of 7.2 millimeters. Might notice here that these equipotential lines aren't evenly spaced in distance like they were for the capacitor. Turns out they're evenly spaced in distance if the electric field is constant. Okay, so this is our set of equipotential lines around a positive point charge. Things we might notice here, why don't we put our electric field lines on first? So we know that the electric field lines are radially out of a positive charge. There's our electric field lines. We'll label those E. The dashed lines are our equipotential lines. Things we might notice here is that our electric field lines are still perpendicular to our equipotential lines, so they're still perpendicular. Our electric field points from high potential, that's inside here, to low potential. Okay, so from 12,500 out to 2,500, so that behavior is still the same. We said that our electric field is strongest where the electric field lines are close together. Turns out the electric field line is also strongest where the equipotential lines are closest. Okay, so let's make a note of that one. Electric field is strongest where EPL for equipotential lines are closest. And then if we were remembering our relationship between field and potential, we would remember that our radial component of electric field is the derivative of the potential with respect to the radial component. If you wish, you can certainly model this on a PhET simulation. I've got one loaded and ready to go here just to show you, but you could work this out for yourself. So if you Google PhET, P-H-E-T, and electric fields, and then to make this graph, what I did was I took a positive charge and I dragged it to the middle. That made my electric field line show up. And then I took my, zoom out a bit, then I took my voltmeter and I put it in the vicinity right here. And I got to a place where I wanted to draw the equipotential line, let's say right here, and I just hit draw. Okay, so you can model those if you wish. You see that the features that we drew on our diagram are the same as the features here. The equipotential lines are close in by the charge, spread out far away. The equipotential lines are perpendicular to the electric field lines, and so on.